Have you ever wondered what happens when a substance heats up or cools down? Why does ice melt when it gets warm? Or why water evaporates when heated? In this video, we're diving into the heating and cooling curve of a substance and exploring how energy changes affect its state. Stick with us, it's a fascinating journey into the science behind phase transitions. Let's start with the basics. What is a heating and cooling curve? It's a graph that shows how the temperature of a substance changes as it either heats up or cools down. The curve represents the relationship between time and temperature, and it's divided into different phases depending on what state the substance is in. In the heating process, as we add energy to a substance, let's say ice, the temperature starts to rise. But something interesting happens when the ice reaches 0 degrees Celsius, the melting point. Instead of the temperature continuing to climb, the heat energy goes into breaking the bonds between the molecules of ice. During this time, the substance remains at 0 degrees Celsius, even though the heat is being added. This is called the latent heat of fusion. It's the energy required to change the substance from solid to liquid without changing the temperature. The curve will remain flat at 0 degrees Celsius until all the ice has melted into water. Now, let's say you continue adding heat. After the ice has completely melted, the water starts to heat up. As the temperature rises, the water eventually reaches 100 degrees Celsius, which is the boiling point. But just like before, something important happens when the temperature reaches 100 degrees Celsius. At this point, the energy that's being added goes into turning the liquid water into gas or steam. This phase change, where the substance transitions from liquid to gas, requires energy called the latent heat of vaporization. And once again, the temperature remains constant at 100 degrees Celsius until all the water has boiled away into steam. Let's shift gears now and talk about the cooling curve, which is the reverse process. Imagine we take that steam and it starts to cool down. As the steam cools, its temperature begins to drop. But when the temperature reaches 100 degrees Celsius, the steam starts to condense into liquid water. During this phase, heat is released, and the temperature doesn't decrease until all the steam has turned back into liquid. This phase change, where the gas turns into liquid, is called condensation. Like melting and boiling, condensation also involves latent heat, but this time, it's heat being released as the substance cools down. Finally, as the water continues to cool, it eventually reaches 0 degrees Celsius and freezes into ice. During freezing, heat is released and the temperature stays constant at 0 degrees Celsius until all the liquid water has turned into solid ice. This is the latent heat of fusion again, but in reverse, the energy is released as the substance solidifies. So, in both heating and cooling curves, we see that there are plateaus where temperature stays the same during melting, boiling, and freezing. These plateaus represents the energy being used for phase changes, not for raising the temperature. Now that we've discussed the concept of heat transfer during phase changes, let's dive into an example problem. Imagine this. You have a block of ice at 0 degrees Celsius and you want to melt it completely into water while keeping the temperature constant. How much heat energy would you need to accomplish this? Let's solve this step by step. Here's the problem. We have a 190 block of ice at 0 degrees Celsius. It completely melts into water at the same temperature. The latent heat of fusion for ice is 334 joules per grams. How much heat energy is required to melt the ice? To solve this, we'll use the formula for calculating the heat energy required during a phase change. The formula we'll use is Q is equal to M times L sub F, where Q is the heat energy in joules, M is the mass for the ice in grams, and L sub F is the latent heat of fusion in joules per gram. Let's list what's given. Mass is equal to 190 grams, latent heat of fusion is 334 joules per gram, and heat energy is unknown. Second, we have to substitute the values into the formula. Q is equal to 190 grams times 334 joules per grams. Next, perform the multiplication. Q is equal to 63,460 joules. Thus, the heat energy required to melt the ice is 63,460 joules. This example demonstrates how to calculate the energy needed to change the phase of a substance using the latent heat of fusion. Here, the energy isn't used to raise the temperature but to overcome the bonds holding the ice molecules together. That's why the temperature remains constant at 0 degrees Celsius throughout the melting process. Now, let's look at another sample problem where heat is used to raise the temperature of water instead of changing its phase. How much heat energy is required to raise the temperature of 50 grams of water from 20 degrees Celsius to 80 degrees Celsius? For this, we'll use the calorimetry formula. Q is equal to M times C times delta T, where Q is heat energy in joules, M is mass of the substance in grams, C is specific heat capacity in joules per grams degrees Celsius, and delta T, temperature change, calculated as final temperature minus initial temperature. Here are the given. Mass is equal to 50 grams, specific heat capacity is equal to 4.18 joules per grams degrees Celsius, initial temperature is equal to 20 degrees Celsius, final temperature is 80 degrees Celsius. First, calculate the temperature change. Delta T is equal to final temperature minus initial temperature. Delta T is equal to 80 degrees Celsius minus 20 degrees Celsius is equal to 60 degrees Celsius. Now, substitute the values into the formula. Q is equal to 50 grams times 4.18 joules per grams degrees Celsius times 60 degrees Celsius. Perform the calculation. Q is equal to 12,540 joules. So, the heat energy required to raise the temperature of the water is 12,540 joules. These two problems illustrate the two key uses of heat energy. Number 1, changing the phase of a substance as we saw in the melting ice problem. And number 2, raising the temperature of a substance as in the heating water example. Both require careful application of formulas and an understanding of the specific heat properties of the substance involved. To summarize, the heating and cooling curve of a substance shows how temperature changes over time as the substance undergoes phase changes. Whether you're heating something up or cooling it down, the temperature doesn't always change linearly. There are specific points where energy is used for phase transitions instead of increasing temperature. I hope you found this explanation helpful. The next time you're boiling water or watching ice melt, you will have a deeper understanding of the science behind it. If you enjoyed this video, don't forget to like, subscribe, and hit the bell icon for more science insights. Thanks for watching and stay curious.